Hello and welcome. Thank you for attending this talk. My name is Gene Pang, and I am one of the founding engineers here and the head architect. In this talk, I'll be talking about the Alluxio architecture as well as how we scale performance for Alluxio, especially in large-scale deployments. Here's a brief outline of what this talk will be about. First, I will go over the high-level architecture of Alluxio. And then I'll go into some of the efforts we've made in scaling performance, especially for large-scale deployments. So first, I'll do a high-level overview of Alluxio architecture, including its components. So here's a diagram of the Alluxio system in the ecosystem. And Alluxio is the data orchestration layer in between compute and storage, as you can see in the diagram. And Alluxio provides an abstraction over the storage systems and also provides a unified namespace and interaction for the applications above. And so this is where Alluxio fits in. And in order to achieve this, there are many different types of components within Alluxio to achieve this data orchestration. So here is a simple diagram of all the various different processes that are involved for the Alluxio data orchestration framework. And I will go through each of them individually. First is the Alluxio master, and this process is mainly involved in managing all the metadata for Alluxio. It manages the file system namespace, it handles the authentication and authorization, which can be pluggable. It also handles the catalog service metadata, such as the structured data for the structured data services. It also maintains the membership information for the other various Alluxio workers in the system. The Alluxio workers are the processes on the cluster, which primarily maintain and manage the cache of the blocks and the files of the system. So here the workers are managing all the metadata required to manage the blocks and files and data. They read and write to and from UFS. So the workers are the ones interacting with the UFS, the under storage systems. And the workers are also responsible for interacting with the clients and other workers to transfer data to and from other parties over the network. The job master is primarily dealing with metadata of jobs. And jobs are these asynchronous and distributed tasks within Alluxio, which can be executed within Alluxio. And some examples are loading the data, writing out the data, persisting the data, moving data around via some policies. So these are the types of jobs, and the job master is primarily dealing with the metadata for the jobs. They manage the execution and the state of the jobs, and they also maintain and manage the information about the job worker membership. And for the job workers, these are processes that actually do the work for the jobs, whichever jobs they might be. And so they run a lot of these parallel tasks on these processes, and they will interact with Alluxio via the Alluxio client. Next, we have the fuse process. And the fuse process is a process that is required to run in order for you to enable Alluxio Fuse. And this is file system in user space. What this allows you to do with Fuse is that users can mount the Alluxio namespace onto their local machine's file system namespace. So it can just be like accessing the local directory tree file system, but you're really accessing Alluxio namespace. And so this process is required for any machine or any node for those nodes to enable this Alluxio Fuse. And within this Fuse process, it uses the Alluxio client to interact with other Alluxio components. And lastly, this is the proxy processes. This is used primarily for the REST and S3 compatible interactions to Alluxio. And internally, within the proxy, the Alluxio client is used to interact with other components of Alluxio. So these are all the various processes that are involved in the entire uh, Alluxio system and for data orchestration. So after that overview of the general high-level architecture, I'll then go into how we scale Alluxio performance, especially for large deployments. So for large-scale deployments, they can provide additional set of challenges for any system. And they will be different from, obviously, smaller deployments. So one set of differences and challenges are just the sheer number of paths and files that are involved. Large-scale deployments typically can get to a large number of paths and files, maybe millions, maybe billions. So this poses a new set of challenges for Alluxio and data orchestration. Another difference is that there just might be a large number of users. And these users might all access Alluxio all at the same time or similar times, all concurrently. So this is another set of challenges that arise when large-scale deployments, Alluxio's deployed in large scale. So after dealing with some of these challenges, we discovered an important thing that we had to deal with in Alluxio, which is obviously we want Alluxio to be fast. So, and what's really important is actually to stay fast, we have to avoid slow pauses. And this is actually very intuitive, but it's sometimes hard to notice and sometimes easy to ignore. And so in Alluxio data orchestration, here are some causes and sources of these types of pauses. First of all, Alluxio is a data orchestration framework for different storage systems. So the actual external storage systems, what we call UFS, they are one source of pauses and slowness. And these include any storage system like HDFS, object stores, cloud storage. There's a lot of different types of storage systems that Alluxio can work with, and they can all, they typically always will go over the network and could potentially cause delay. In the same vein, there are external metadata, structured data like metadata and catalogs that Alluxio interacts with, what we call UDB. And they also will have to go over the network, and sometimes they may be overloaded. So they also will cause some sources of delay. And lastly, even if the network is not involved, even local disks, which require I/O, they can also be a source of slowness and pauses, such as SSDs and hard drives. So these are different types of sources that contribute to some slowness in Alluxio. So in the following slides, I will talk about some of the recent changes we've made in order to address these specific pauses. So the first one I want to talk about is how we do metadata sync and the log contention related to it. So metadata sync is something that Alluxio performs in order to sync the namespace of the UFS with the Alluxio namespace. This has to happen sometimes, and how it happens is that a request comes in, and that thread will have to lock the namespace that it wants to sync, and then during that lock, it will have to access the UFS, and then and update the metadata, if any, in Alluxio. So during this time, it has the right lock. So when other threads come in, the other threads will not be able to access that portion of the namespace because it has been write locked by the first thread. So it has to wait for the entire duration of that sync in order to continue on. And so this can be problematic for several different reasons. Number one, the sync itself is single-threaded, so it can just take a long time for a large subtree of the namespace. It also requires the write lock for the entire duration of this part of the sync. So it could take a long time. And this long time holding the write lock can block other threads from making useful progress. So in order to fix that, what we did was first we reduced the time. We reduced the time holding that is required to hold that write lock. So we removed some portions of the sync to outside that write lock. And then in addition to that, we parallelized the UFS access during that sync. So what that will do is it will actually speed up and be able to more quickly retrieve the information from UFS and more quickly update that data in update the metadata in Alluxio. So what that really means is that the portion of time that is write locked for that thread is much shorter than it was before. So even though when other threads come in and are blocked on that write lock will be released much more quickly than before, allowing other threads to eventually make progress sooner. And so by shortening this critical section with the write lock, we can allow far more concurrent users and even enable faster syncs because of the parallelized syncing. Next, I'll talk about how an issue about slow data reads from the UFS. And so in this scenario, this is typically seen, this is more often seen when there's like a lot of parallelism and a lot of concurrency, a lot of concurrent users. And so what would happen when a client wants to read data from UFS is it would ask the worker to read from a file, and then the worker will then read from UFS. But that could be slow depending on how many users are doing the same thing. And when that happens, even though the UFS is responding with data in the correct way, it just happens to be slow, the client will time out and cause some error for the application. And so ultimately the application will look like it failed because the timeout thinks, the client timed out and thinks something failed with the read from UFS. When in actuality, the UFS is working properly, it just happens to be slow during that time. So in order to fix that, we have to expect that UFS will be slow sometimes. This is not something that we can avoid since it is an external storage system that we have to deal with. So instead, we have to deal with the slowness in a better way. And how we do that is to better handle these delays on the client and on the worker. So because we have to expect some slowness, we have to adjust how we handle these types of timeouts so that we don't produce an error just because it took too long. We only have to produce an error when there actually was an error during the read. And we also added some logging for better observability of what's going on when certain things are slow. And so what this really helps, how this helps users is that it prevents unnecessary timeouts on the client. So it prevents unnecessary failures in the application. And this is especially helpful in high concurrent workloads. Next, we'll talk about how there were some improvements in the catalog syncing. So in the structured data services, the Alluxio catalog maintains the metadata for structured data and tables, and it needs to access data from other external catalogs such as Hive Metastore or Amazon Glue. So what happened is the client would ask the catalog to sync, and then the catalog will just sync from the UDB, and it'll just do it in a single-threaded way, and then return back to the client. And so this, if there's a large database or many tables or many partitions, this can take a long time to complete, and it can be a negative experience for the client. So instead, we can improve that by allowing a configurable number of parallelism for when we update the catalog in Alluxio. So by simply being able to parallelize that access, we can greatly improve the syncing speed, especially for large databases and large tables and with many partitions. Next, there has been a lot of work in how we deal with disk I/O in worker tier storage. And so in Alluxio, we have the concept of tiered storage where we can cache data in different types of storage medium, such as memory, SSDs, and hard drives. And the data could be in any one of these tiers. And ideally, we try to keep the most important or most important data in the top tier because those are typically the fastest. So before, what would happen is when a client comes in and wants to read a piece of data, that block is identified. And here, we identified it's in the second tier, the SSD tier. And the default mode is in cache promote. And what that means is it'll promote or move the block to the top tier whenever it's read in order to keep it in the fastest tier. So in order to do that, this block on the SSD tier needs to move up to the memory tier. But if that's full, we need to kick something out. And so we identified a block to kick out and move down to the second tier, SSD tier. But that tier is also full currently. So we have to identify a block to kick out. So we identified a block to kick out. And then lastly, the last tier is also full. So we need to identify another block to kick out. And so once all of this happens, that's when we can start kicking all these blocks out. We can move all the tiers down, all the blocks down the respective tiers, and then finally move up the block that we really wanted into the top tier, and then finally service and return back to the client. So there, in that example, there have been many disk IOs, lots of reads of disks, lots of writes of disks, lots of moving of blocks. And so just for a simple reading from the client of a block that is already cached in Alluxio, many instances of disk IO were required. And this can actually really slow down a read, even though it's cached in Alluxio. So instead, in the new implementation of this, after we have identified a block to read from the client, we immediately read it and send it back to the client. So we don't wait for anything else. This is just the normal cache mode of reading, not the cache promote. So cache promote is no longer the default for reading for this purpose, for this goal. And then once that's been serviced asynchronously, so the client doesn't have to wait for this. So asynchronously, in the background, the blocks will be moved around so it's appropriate and matches the caching policy for the Alluxio worker. So in the background, the correct blocks will be moved up to the right tiers, and the other blocks will be sort of evicted out and moved around. And so all of this is done in the background and asynchronously. So the client does not have to wait for all of this disk IO. And so since the client does not have to wait, it will be much faster for the client, and it will also provide a more predictable performance for Alluxio disk IO. And in this example, this is related to the client-side data cache in Alluxio. And the client-side data cache uses the local disk to store the cached data. So the client can do gets and puts of various data to the local storage. And so what will happen is the client will call something, but then if that disk is maybe overloaded or it failed or something, it might take a long time to return to the client, or maybe may not return anything at all, just wait for a really long time or forever. And so in these examples, like in these cases, the client could potentially just wait forever. It'll look like the application hung, just waiting for something from the local cache. And that can be, clearly that's a negative, that's not a great experience for the application. So instead, we have to be able to handle something like that well on the client. So instead, even when responses don't come in time, we have to be able to handle that. And so we have a configurable timeout for these operations of the local cache. And this allows the application to avoid unexpected hanging of the entire client. Instead, the client could just say, could just return that there was a timeout in getting that data, in accessing that client-side cache. So those were a lot of the recent improvements we made, all related to um, how we scale out to large scale deployments. And so what we've ultimately concluded is that, Alluxio data orchestration, it can be pretty complex, especially since it needs to interact with external storage, whether it's over the network, whether it's local to the machine. There's always going to be some sources of pauses. And so the main conclusion is that we have to expect that slow I/O is going to happen, especially when we talk to these storage systems. And if we have this mindset, there's basically two main things that we need to always keep in mind for Alluxio. First one is we cannot force users to wait for this type of slowness. Since we have to expect the slowness, we shouldn't make the users wait for the slowness. And secondly, because we have to expect slowness and pauses, we have to handle them appropriately. We have to deal with them in a user-friendly way. And so by having this type of philosophy in Alluxio, the way that this will really benefit users is that Alluxio will be faster, Alluxio will be more predictable performance, and it'll also allow more concurrency for the entire system. So thank you for this talk. This is what we learned in the past, the recent work that we've done in scaling performance for Alluxio in large deployments. Thank you.